All right, everyone. So what we're going to focus on in this module is some introductory vocabulary and some review of some wave mechanics in order for us to start talking about light or electromagnetic waves. So what we've done so far in the last two chunks of the course is we've explored electric fields and how they behave, and we explored magnetic fields and how these behave. And then what we started to do, especially in our magnetic field sections, is we started to couple these two together and see how they affect each other. Well, now we're going to bundle these together and we're going to refer to their fluctuations that are dependent on each other as electromagnetic waves. Okay, so now moving into this section of the course, this is all about light, the mechanics of light, how its properties arise, and some of the properties of light that come from traveling through different mediums or in different situations. So just a few things to start off is that these fields are my electric and magnetic fields are coupled, okay? And when we start talking about these fields that are coupled, these fluctuations or disturbances in electric or magnetic fields that now are going to be coupled, we're going to talk about these with some vocabulary that we've seen before, maybe in Physics 1, but we want to review it here to make sure that we know what's going on in order for us to talk about light in this way. So the first thing is frequency or wavelength. Okay, these two things are coupled to each other. And the second thing is going to be wave speed. So in order for us to talk about wave speed and frequency and wavelength, we need to define a few things that are common for light. So the first thing that I want to introduce here is my speed of light, right? This is my wave speed for light, for my EM waves, okay? And my speed of light here, we're going to start with this definition in vacuum, okay? So this will be sort of the original speed of light that we're going to work based off of. And this, okay, so I'll put in vacuum. So this works, in space. The speed of light is 3 times 10 to the 8 meters per second. And I'm going to label this as C. Okay, so this speed of light, we're going to label it as C. This will be the variable for the constant that we use for our speed of light. Now, so if we want to know what the wavelength of any of these electromagnetic waves are, just like before when you guys have seen waves maybe in Physics 1, we need to use this formula right here. So this will say lambda, which is my wavelength, okay? So this right here is my wavelength. And this is literally, remember, this literally means the length of my wave. So, I have my wave drawn here. If I have this wave, remember my wavelength in space literally means how far is it from one end to the other of my wave, right? So from here to the end of my wave, how long is this? And this is only one full wavelength, okay? So in this picture here, we have a bunch of oscillations, so don't take the length of the entire thing when you're looking for wavelength. We only want one entire wavelength, which means, one crest and one valley, something like this. So we need to know our wavelength, and here we need to know this is our wave speed. How fast is our wave traveling through space? Okay, and then the last thing here is frequency. And frequency, if you remember, we have a special unit for this. This is 1/seconds, which is nicknamed as hertz. Oops, let me go ahead and try this again. Hertz. Okay, so now that we have this, remember my wavelength is a length, so its unit is meters, and my wave speed is meters per second. Okay, Now that we have this, we can write this out for light. So for light, this would be, okay, my wavelength is going to equal to c over f. Okay, so it's just a constant. So we have 3 times 10 to the 8 over f. So for any wave, if we want to find its wavelength or if we want to find its frequency, all we need to know is the other parameter. And since we'll be counting light as always traveling at this speed, then we're going to be using this formula right here. So how we would do this in this example, we want to know what is the wavelength of a 1 kilohertz wave. Okay, so this is its frequency is 1 kilohertz, 1000 hertz. All we need to do is write out this formula with 1 kilohertz, which is, remember we have to always convert to our standard units. Oops, this will be 1000 hertz once I've converted from kilohertz to hertz. Okay, so this should give us 3 times 10 to the 5 meters, right? So here we have our wavelength. If it's a 1 kilohertz wave, then this is its wavelength, okay? Some 30,000 meters. Okay, so what we're going to do now is, okay, now we're going to look at the distance covered by light in vacuum. Okay, so this is just another way we're going to bring back some previous topics from Physics 1, except now we're going to be using them in the context of light. So the only thing, we have this very trusty formula here. Remember, my velocity is the displacement over time. We're going to use this now for light, and our light is just going to replace my velocity with c. So c will give me my displacement covered over some time. So let's say now that I have 1 microsecond, or 1 times 10 to the minus 6 seconds. Well, how far does light travel in that amount of time? Okay, all we would need to do is, in this formula right here, we need to find our displacement when our time is 1 times 10 to the minus 6 seconds. Okay, so multiplying both sides by 1 times 10 to the minus 6, what we'll get is our displacement here will be 1 times 10 to the minus 6, okay, times 3 times 10 to the 8th meters per second. And this here should give me, okay, let's go ahead and calculate this. This will be 3 times 10 to the 2, I believe. So we've got 300, right? So in 1 microsecond, my light will travel over 300 meters.